Hello students, in today's class we will learn about the electric flux. What is electric flux? We will be defining it first, and next to that we will try to find derive a formula through which we can find the numeral value of the electric flux in a given system. So let's get started. The first point here suggests us about the liquid flow. A liquid which is flowing through a given surface area passes through that, and the liquid, when is a broad liquid, like the liquid is coming from this tap, from here, and we have placed something as small as a ring as a surface area over here. Only the three lines are able to pass, this one and this one and this one. So for this particular surface area, the amount of liquid which is able to cross it is called its flux of liquid. So let's read the first statement. Consider a flow of liquid with velocity v through a small flat surface, that is ds, in a direction normal to the surface. Direction is normal to the surface. If this is the surface in this direction, this is the direction which is making a 90-degree angle with it. See, this is the direction making 90-degree angle, that is normal. Rate of flow of liquid is given by, this rate of flow of liquid is the flux of liquid, is given by volume crossing the area per unit time, and represents the flux of liquid flowing across the plane. So this thing gives us the flux that is flowing through that particular plane. So rate of flow of liquid. How to define rate of flow of liquid? Volume crossing the area per unit time, that gives us the flux of our liquid. Now the second point here states that if this angle of this surface is changed by some theta degree, see, this is our flow of liquid, and our surface is here. If there is a change in the angle, at present it is 90 degree, now this is theta degree, and it can be like this also. This gives us another theta1, theta2, we can write that. So angle is changed. Once the angle is changed, the flow will be reduced. The amount of liquid passing through the given surface will be less when compared with the angle made is 90 degree. So you can check it at your home. Open the tab of your kitchen and just place a bottle perpendicular, like parallel to the surface. See, this is flow and this is our bottle here, like this. If you are placing it like this, the whole water will go inside the bottle and it will fill. But when this is the flow and your bottle is like this, what is the amount of liquid that will go inside? Only this amount will go, remaining will go down. Okay, only this will start filling up the bottle like this. So when you change an angle, there will be change even in the flux or in the amount of flow of rate of that liquid. So this is on the basis of liquid when we are defining liquid. So why we took the example of liquid in first 1 and 2 statement? Why? Because we want to know what is the flux and what is the electric flux. We know the flux now, amount of the liquid that is flowing through the given area per unit time, that is our flux of liquid. Now similar way, electric flux, the amount of electric field lines that are able to pass through a given surface area is will be giving us the electric flux. So see the second statement, it states normal to the surface is not parallel to the direction of flow of liquid, that is v, but makes an angle theta with it. The projected area in the plane perpendicular to v vector is del ds theta. Therefore flux going out of the surface is v and ds. Here n is a unit vector. Unit vectors are usually to provide us or to define for us direction. They define direction for us. Okay. Now the third statement, number of field lines crossing a unit area placed normal to the field at a point is measure of the strength of electric field at that point. See here, our electric field lines are going like this. See figure 1. This is figure 2. Here field lines are going in this direction straight, and this is our surface area, some kind of area we have placed to measure how many electric field lines are passing through it. So both are in the same direction. This area is making 90 degree with electric field, but the vector of this particular area is parallel to electric field. See, del S is going in this direction, electric field is going in the same direction. So they are parallel to each other. So in this case, the amount of electric field line that is passing is maximum. While in the second case, this is our second case, here our surface area is same, like length of this is same, but it is tilted, tilted to some angle theta degree. So what happens? The amount is not maximum, Here the electric flux is reduced. Once we changed our surface area's angle with respect to the electric field lines, we found out that our electric flux is reduced. Now this means that if we place a small planar element of area del S normal to E at a point, the number of field lines crossing it is proportional to E del S. Number of field lines, I will write over here, number of field lines crossing is proportional to E dot del S, and both E and del S are vectors. Always remember, because we are going to be go for a vector product. Now suppose we tilt the area element by an angle of theta degree, clearly number of field lines crossing the area element will be smaller. Of course it will be smaller, as explained previously. Projection of the area element normal to E will give us del cos theta. This is our surface through which these electric field lines are passing. So this have one projection over here and other projection over here. This projection is of no use. We will take always this projection. This projection will give us, as this is a del S area, this projection will give us del S cos theta. So it has given us del S cos theta. Now number of field lines crossing del S is proportional to E del S cos theta. They are proportional to this, because see, electric field lines are coming from here, they are parallel to this, and hence with respect to this only we can find out the amount of lines which are passing through our surface area. Now when theta is 90 degree, field lines will be parallel to del S and will not cross it at all. Now this is our surface and this is del S cos theta, and these are electric field line E. Once we are changing angle theta 1, theta 2, theta 3, and similarly at a point at a point it comes to del S cos 90 degree. The theta became 90 degree. What is the value of cos 90? Cos 90 is 0. At this point, lines which are passing through del S will be 0. The lines which will pass through the given surface area will be 0 once the theta is made 90 degrees. The orientation of the area element not merely its magnitude is important in many contexts. What this line aim at saying is that at which particular angle and how our area vector is oriented is also very much important, not just the magnitude of that vector. Like magnitude can be very big. You have a tanker full of water, but if you are not refilling your bottles properly, then the whole water will be wasted. In the same way, if when we are calculating electric field lines, our surface area, the surface area which we choose is not properly oriented, then there will not be a proper calculation. Okay, so now example is given here, the same example which I have already told you, that is in a stream the amount of water flowing through the ring will naturally depend on how you hold the ring, how you hold the ring. See, when ring is normal to the flow, maximum flow of water rather than any other orientation, this shows that area element should be treated as a vector, because direction is also important. That's why they are saying that area vector, area element is also a vector. It has magnitude, of course, which we are seeing, as well as direction also. It depends upon orientation. The normal to the plane specifies orientation of the plane. Thus, the direction of the planar area vector is alone its normal. Alone its normal. So, planar area vector is this and normal to this plane is this. So, in this direction we define the vector of area. Vector of area. Defined normal to area or normal to surface area. Normal to surface area. Okay. Now the question arises, how to associate a vector to the area of curved surface. Now we have seen this is our triangular face, this is our square face, this is rectangular face, this may be our triangle face. We are having this, we know area of these also, area we know. Area of triangle is half base into altitude. The area of this rectangle is B into L, and for this we have A into A. So we know area of these shapes. So it is not very much tough. Area of regular shapes. But when it comes to the curved surfaces and irregular surfaces, how can we find out the vectors of area associated with them, and how can we find out the area also? So see here, we imagine dividing the surface into a larger number of very small area element. We will define this into very small areas. This is our area. We will just cut it into many small areas which are approximately rectangle or square, and hence it will be very much easy for us. Each small area element may be treated as a planar, it's a plane, and a vector associated with it. So see, I'll give you the universal example, that is in a circle. If we cut this circle into small pieces, we will find that it is made up of infinite lines. It is made up of infinite lines. So what does a circle is? It's a shape which is taken by the merging of infinite lines, so we are not able to identify the corners of a circle. So similar way, in a curved surface, if we are dividing this into many small parts, we will find that each and every element is looking like a plane. So what is the ambiguity over here? The direction of an area element is alone its normal. Direction is always alone its normal. See, this is area vector and direction is at a 90 degree to this. Okay. But normal can point in two direction. This normal can point in two direction. Here also, in this direction also. Okay. So now, hence which direction to choose? The question, second question arises, which direction, which normal direction of the area element should be chosen? The vector associated with every area element of closed surface is taken in the direction of outward normal. Always we have to see that we are taking a outward normal instead of taking the inward or sideward, always outward. In this particular area, we have to choose this area and then these vector lines. If this is the area, we don't have to choose these lines, we have to choose these purple color lines. See, in this, these lines should be chosen. So always outward and normal, it should be going out to the given surface and it should be normal at 90 degree. The area element vector del S at a point on a closed surface is equal to del S into n cap. Why n cap? Because area element is a vector, and for this particular area element, del n gives us direction. It gives us direction. Now del S is the magnitude of area element and n is the unit vector normal and outward. Electric flux through an area element del S is defined by del xi equals to E del S, which will give us E del S cos theta, which is proportional to the field lines cutting the area element. Here angle theta is the angle between electric field and vector component of area element. Unit of the electric flux is given as Newton per coulomb meter square. Newton meter square per coulomb or Newton per coulomb meter square. Meter square is not in the denominator, it's in numerators. Okay. So now I will give you a concise summary of what we have read in the electric flux. See, first of all, we have seen flux is the electric field lines passing through given surface area. Okay, this is definition for electric flux. Now we have these lines and they are passing through this particular area element. Okay, this area element is given by del S. That is a small angle, a small area element. We haven't taken the whole area yet. So when we will take many areas, it will simply be S. Now the formula for flux is it is given by electric flux xi equals to E electric field dot product and to surface. Now the dot product is removed, we will get E del S cos theta. Now cos theta here defines angles at which E and S will be. Theta is a angle between electric field lines and surface area or area element, surface area element. Okay. So when there are cases when theta equals to 0, cos theta will become cos 0 and cos 0's value is 1. So it will give us maximum flux E max, that is xi max, that is E del S, when theta equals to 90 degree, cos theta will become cos 90 degree. That will give us value of 0 and flux will be minimum, that is xi minimum 0. But when theta is between 0 to 90 degree, it have a range of E del S cos theta, which ranges from maximum value to minimum value. Maximum to minimum value. Hope you understand the formula for the electric flux, how the theta is a defining property. So, from here we get to know both these are vectors, and this is also a vector because it provides us direction as well as magnitude. Now, next to it which we need to understand is how we are taking the angles. See, this is our surface. This is our surface through which we need to pass these many electric fields, which are coming. These needs to pass through this. So, they will pass. Now, this area vector, area element will give us two direction. This is our element. This element will have a flow, will have a direction in this path as well as a direction in this path. This will be given by the sine component and this will be given by cos components, but this is of no requirement, no such requirement, only this will be taken as the requirement. This particular direction is given as del S cos theta, and these electric field lines, if you will extend, you will find that these are parallel to each other, parallel to each other. Parallel to each other. Hence, they have theta equals to 0. Now, if there is a change in direction like this, it is making some angle theta. The theta will be some angle. And when these two are at some angle, these electric field lines will pass lesser in number from the same surface, and hence the flux will become less. Secondly, in this particular surface, we got this particular surface. From this surface, this is our circular surface. First thing which we need to know is we will divide this surface into many small components to make it planar, small components, and will make it planar. Then other thing is which direction we need to take. This is our surface here. We need to find the flux from this surface. The 90-degree normal to this surface will be this, even this, and in some other direction also, like this also there will be some normal. Okay, which normal should we take? To surface area element, the normal which is outward should be considered as the direction vector of area, that area element. Okay, so that's the summary of today's class. That's all for today's class. I hope you understood what is electric flux, how we are defining electric flux, at what condition it is maximum and at what condition it is minimum. Go through the last slide. It is just a concise version of the 3 slides we have read so far. And okay, so bye bye, see you in the next class.